So I'm talking about the generalization of directed graphs in terms of perfect matchings. And of course, the question is, why would we do this and what are we going to do with it? And so let's go for some motivation. And we start out with the undirected case. So in undirected graphs, we already have a very nice notion of decomposing graphs into tree-like structures. And we also have a generalization of what a subgraph is, which is a minor. And then we have the grid theorem, which states if we have a large tree width, then we get a large grid minor. So this can be generalized to directed graphs. And here it gets a little bit more messy. We get a strange new notion of what connectivity is, which doesn't really use the same monotone structures that we had before in the undirected case. Now it can happen that you delete a vertex from somewhere in the graph and you lose connectivity somewhere else. And also the minor notion gets a little bit more messy. There are several different notions, and what we use is the butterfly minor. So now we are only allowed to contract directed edges such that these are the only incoming edge of their head or the only outgoing of their tail, which is done in order to prevent new paths that haven't been there before from coming into existence. And recently, we have gotten a grid theorem here as well. So now we know that if we have large directed tree width, we can find, as a butterfly minor now, a large cylindrical directed grid. So next up is basically the next step. We want to go from directed graphs to graphs with perfect matchings, which are now, again, undirected. We already have a notion of decomposition, which I won't go into detail over. But now we have a problem. As you can see, it looks more like edge cuts than real separations here. And this is because now, for given a perfect matching, the line between vertices and edges begins to blur. We will see later how this happens. And of course, we again have some notion of what a minor is. And now we have to be more careful. We are only allowed to contract two edges at once because we want to preserve the property of perfect matchings being in existence. And we are only allowed to contract exactly the two edges that are incident with a vertex of degree exactly 2. And this is what we call a bicontraction, and the result is a matching minor. And it comes of no surprise that connected to this, we have, again, at least the conjecture of a grid theorem. So if we have large perfect matching tree width, we hope to find a cylindrical grid as a matching minor. How to tackle this problem? That's the question. So if you look at the proofs for both the undirected and the directed grid theorem, you will see that usually it's connectivity that matters. So you look for substructures that use high connectivity, a lot of paths that you can just intersect with each other that give you the grid. And this raises some questions. Basically, what is connectivity in the matching setting, and what do paths look like? Luckily, we can get some intuition from directed graphs. And the next slide is going to show you how this is done. So this is a construction introduced by Robertson Seymour in the late 90s. You take a bipartite graph and fix any perfect matching together with a bipartition. So we have U and W, and we have the yellow edges as a perfect matching. And then you take all the edges that do not belong to the perfect matching, so all non-yellow edges, and you just orient them from U to W. And then next up, you simply contract all the perfect matching edges into vertices. So this is where we can see why the line between edges and vertices begin to blur, because the perfect matching edges somehow are the vertices of our graphs. Okay, so next up we want to know what a path is. And for edges, this is already clear, right? And a path of length 1 is basically an edge starting at the vertex of U, ending in the vertex of W. And if we look at the directed graph here, a path is simply an extension of this, hitting in between these edges, these vertices that were edges before. So we're looking at alternating paths that start on an edge that is not part of the perfect matching and end on an edge that's not part of the perfect matching. So what we get is exactly this, an extension of an edge. We start at the vertex of U, end on the vertex of W, and in between every second edge is part of the perfect matching. And such a path, in general, not only in bipartite graphs, is called a weakly extendable path by us. It's just a technical term that we used during the research meetings. So doesn't really have a meaning. No, not yet, at least. But these things can be used. So now next we need a notion of connectivity. And what we do is we say the graph G, having a perfect matching, is connected if its cover graph, noted by a curve of G, is connected. And what is the cover graph? Basically, we take our graph and throw away all the edges that do not belong to perfect matchings. So all edges in G belong to at least one perfect matching of the graph. And if this thing is connected, the graph is called matching connected. And as it turns out, we can give a characterization of this connectivity in terms of weakly extendable paths. And this means if you give me two edges of my perfect matchings, you will find a weakly extendable path, like the blue one here, connecting one endpoint of E1 to an endpoint of E2. And you will also find a second weakly extendable path connecting exactly the other two endpoints of these perfect matching edges, which is, of course, what you would expect if you look at directed graphs, right? A directed graph is strongly connected if you start at a vertex, find a path to another one, and then you find a second path going back. And so it comes of no surprise that a bipartite graph is matching connected if and only if its directed version for any perfect matching is strongly connected. So here, the things somehow line up. The next thing we want to look at is minors. Right? We have this notion of butterfly minors, we have this notion of matching minors, and we want to bring them together. So we take a bipartite graph G, and we take a matching minor of it H. And as it turns out, you can find this, at least one perfect matching that somehow describes how we can get from G to H. And this perfect matching will somehow be represented in H as well, so we will have some residue over. And taking M, we can also find, since G is bipartite, this M direction, this directed graph hidden within G, corresponding to M. And as I said, there's a part of M left over in H. This we can also use to get the direction of H. And it turns out these two graphs are also connected, because this one here will be a butterfly minor of the first above. So now what we have is we know what connectivity is, we know what paths are, we also have aligned minors. So what's going on? We want to build a whole theory. We want to, at some point, reach the grid theorem. So the next question is, what else can we generalize? And also there's already a theory of graphs with perfect matching in existence, and we want to somehow fit our theory into this canonical matching theory. So for the first problem, we already have some results. And the first one is we can extend this matching connectivity to higher levels, matching N connectivity. And for weakly extendable path, there's also a Menger-like result on it. And second of all, if you look at directed graphs and look at their strongly connected components, you will have a topological order on them. You will have a first one, you will have a last one, and things in between. And something like this can be done in the matching case as well, even on non-bipartite graphs. But it looks messy. Everything gets more technical. And for the second part, and this is maybe just for the people who know a little bit of matching theory, we can find a link between N extendability, which is a parameter studied in matching theory, and our matching N connectivity. So there are just a few classes where these two parameters don't line up. And also we can characterize the two building blocks of graphs with perfect matchings, braces and bricks, where braces are the bipartite graphs, via a weaker notion of matching connectivity. And now is the question, what comes next? So the first project would be to lift directed tree width to perfect matching tree width. And aligning with this, we also ask the question, how can we translate abstractions for directed tree width to the matching world? Especially we are interested in a cops and robot type game. And the second project will be more on the canonical side, so we want to look further into bricks, because for braces everything is pretty much easy. Bipartite graphs are in fact directed graphs. And we also want to look further into the N extendability, because there are some gaps that we haven't closed yet. And these we hope to close via matching minors. So thank you, and I'm ready for questions.
Okay, thank you. Any questions? tell more about the characterization of bricks and braces that you mentioned?
So as we have seen, strong connectivity and matching connectivity are basically the same. And this stays the same for higher levels. So matching and connectivity is the same as strong and connectivity in directed graphs. So for braces, it's basically you're a brace if and only if you're matching two connected and the cover graph is bipartite. And for bricks, it gets a little bit more complicated. So there are matching one connected bricks, but you can define a certain type of matching separations that preserve some cuts, some edge cuts in the graph. And if you look only at these separations, which is our weak notion of connectivity, you will end up that in the bipartite case, this is still the same as matching two connectivity. And in the non-bipartite case, this will give you now two separations. So in this weaker notion, bricks are matching two connected.
Any other questions? Just another question. So there's these, for minors, there are these theorems that if you have a highly connected graph, it's going to contain your favorite minor. So you fix KT, and then if it's F of T connected, then you get KT as a minor. I was wondering if something like that might be doable in the matching set.
At some point we were thinking about this, but basically what we came up with is we don't know enough about this yet to give a real good statement about it. We hope to find something like this in the future, but we're not even sure for directed graphs. So there is this conjecture that you can find in highly strongly connected directed graphs a large crown as a butterfly minor, but not even, as far as I know, this is still open.
Okay.